All right, so post hiatus, welcome everyone to GOCC. We've got our first talk of August by Stephan Pfannerer. So everyone enjoy.
Okay, thank you for the introduction and thank you for having me here. It's quite a pleasure that I can present this result. That's kind of my lockdown result because I conjectured it when lockdown started in Austria, and I was finally able to prove it when lockdown was over. And then, as I've told some people already before, I immediately wrote to GOCC because I wanted to give a talk about this before writing the preprint to get early feedback. And I think this seminar will be a great opportunity for this. So this title says that I will talk about a refinement of the Murnaghan-Nakayama rule by descents for body strip tableau. So this will mostly be a story about various kinds of tableau. To start with, we need a notion of an integer partition, which simply is a weakly decreasing sequence of positive integers that sum up to n. And usually we like to draw this stuff in terms of so-called Young diagrams. Let's look at this example here. We take the partition 4 to 1. This is a partition of 7 because it adds up to 7. And we draw it in this Young diagram. That means we have 4 boxes in the first row, 2 in the second, and 1 in the last one, corresponding to 4 to 1. Here on the left is English notation. There's also French and Russian notation. But for the first half of the talk, we will stick to English notation. If we have 2 partitions, we can compare them. One of them could be contained in another one if all the parts of one of the partition are smaller or equal than the parts of the other one. And we use this to find skew shapes, which simply is we take the cells from the bigger partition and subtract all the cells from the smaller partition. So when we take this partition, draw it in here and delete everything, then we obtain this shape here. This is what we call a skew shape. And in particular, this skew shape is special because it's connected and does not contain any 2 by 2 rectangle inside. So what we call these special skew shapes is border strips, and they are also known as ribbons or rim hooks. So later I will talk about border strip tableau, but you could also call them rim hook tableau. There are all the names in the literature. And there's an important statistic related to these strips, namely the number of rows it spans minus 1. So in this example, this one spans 6 rows. We subtract 1 and get 5, and this is what we call the height of the strip. Now we come to our first tableau, which are the standard Young tableau. I guess many people here in the audience know it, but I will define it anyway. So we take our Young diagram and we fill it with the values from 1 up to n, each one occurring exactly once, so that the values in the rows and in the columns are increasing. So as we can see here, if I go from left to right, the values are increasing, and if I go from bottom to top, the values are also increasing. And if we want to talk about all standard Young tableau of a given shape, then this is the SYT of Lambda. There's an important statistic on standard Young tableau, which are called the descents or the descent set. This is defined as follows. We look at the position of I and compare it with the position of I plus 1. And if I plus 1 lays somewhere below, then we say I is a descent. So let's look at the example here. We compare 1 and 2. 2 is next to 1, so 1 is not a descent. If we look at 2 and 3, 2 is above, or otherwise 3 is strictly below of 2, so 2 is a descent. 3 is not a descent because 4 is above. 4 is not a descent because 5 is right next to it. 5 is a descent because 6 is here somewhere below, and 6 is not a descent because 7 is above. So here in this example, the descent set is 2 and 5. And also quite important for this talk is the so-called major index, which is the sum of the descents. And of course, we are interested in generating functions. So we look at the sum over all standard Young tableau of a given shape and calculate q to the power of the major index of this polynomial, add all these up, and this is what we call the major index generating function. And this is also known as Lustig's fake degree polynomial, and we denote it with f lambda q. Let's calculate this on an example. I will often use this partition 2 to 2 for small examples. So here are all 5 standard Young tableau of that given shape, and in orange highlighted are the descents. And if we look at the major index here of this tableau, we have 1 plus 2 plus 4 plus 5 giving 12. So in total, we have q to the power of 12. And we do this for all other tableaux as well. We add them up, and this is f lambda of q. So far, so good. Now let's do something that may appear a little bit crazy. We want to plug in nth roots of unity into f lambda q. So in this example, n is 6, so we'll plug in 6 roots of unity. And so we can choose primitive roots. We choose the primitive 6th root, the primitive 3rd root, the primitive 2nd root, which is also -1, and the primitive 1st root, which is just 1. So if we plug in just 1, of course, what we will obtain is, if we plug in 1 in this generating function, we will get the number of summons in here, which of course is just the cardinality or the number of standard Young tableau that we have here, which is in this case 5. It's also quite easy to do the 2nd root of unity because this is -1. So we have 1 plus 1 minus 1 plus 1 plus 1, 1 cancellation, so we get here 3. And if we do the other ones, maybe with help of Sage or your favorite other computer algebra system, we get 0 and 2. And something that combinatorialists always like to realize is that when there's something, an integer, that there should be a combinatorial interpretation of these numbers. And in fact, there is a nice interpretation, and this is where the border strip tableau come into play. So let's define them next. So a border strip tableau, here we look at the example, tile our shape with border strips. And in this case, I want them all to be the same length, namely k. So there will be in total n over k such strips, and we fill these strips with the values 1 up to n over k, such that then in each row and in each column, the values are weakly increasing. So this is a border strip tableau with strip length k, in this example 3. We denote the set of all of them with this BST lambda k. And one thing that you should notice is if we choose the strip length to be 1, the strips of length 1 are just single cells, so we obtain back the standard Young tableau. So border strip tableau with strip size 1 are just standard Young tableau. And one notation that we will use is the notation of lambda having an empty core. For people that know what the core is, the following is equivalent. Lambda has empty core if and only if there's at least one border strip tableau. For people that don't know about the core, simply see this as a definition for having empty K core. So this tableau here, or this partition has empty 3 core, and here's an example for a border strip tableau. Let's look at our example again and look at the border strip tableaus with strip size 1. I've already told you these are just the standard tableau. We had them before, and they're precisely 5. So this is the number here, and this is no surprise because when we plug in 1, then we get the number of summons, as I've already told you. If we look at k equals 2, we get something that we also call domino tableau, and there are precisely these three guys here. And if we compare with the result from the second root of unity, we also get here a 3. If we plug in 3, so strip length 3, we get these two tableaux and had as a result 2. And if we would look at border strip tableau with strip size 6, of course there are none of this shape because we cannot find any way to tile this with 6 strips. So we also get 0 and have this non-empty core here. So this is of course not a coincidence. This is something that's a theorem that's fairly old already. And I will tell you a little bit about the meaning of this, and this is coming from representation theory. So if we...
I have one question, just sort of a random thing. So is it possible that you can get a border strip tiling, but it would be impossible to label it with numbers? Or if you can get this tiling, is there always a way of putting the numbers into it?
So the definition for the border strip tableau is that we always need a labeling in there, but I think you can always label it because you kind of have a most right or most bottom tableau or strip that you can remove. And in this, you will put the largest entry. So I think that there's always a number.
Yeah, and that I assume that there can also be multiple numberings in some cases. So those would count as different tableaux.
Yes, of course, there can be multiple numberings. Not in this example.
Yeah, not in this example, but in the last one, I think there were.
Let's look at this one here. So here, 6 and 7 could be exchanged.
Cool.
So
thanks.
the labeling is not unique. Okay, so the reasoning behind this comes from representation theory of the symmetric group. And for this, if we look at the irreducible characters that are indexed by partition, so we take this chi lambda, and we want to evaluate this at a conjugacy class that's also given by a partition because it's coming from the cycle type of a permutation, then there's one famous result which is called the Murnaghan-Nakayama rule, which says we can calculate the character values by looking at the sum over some border strip tableaux. Now they don't have all strip lengths equal, but some strip lengths according to the partition rho. And we have just ones and minus ones that we add up here. And we add the sum of the height of the tableau. And the height of a tableau is the sum of the heights of its strips. So this is either 1 or -1. And there is a nice result by James and Kerber from the 80s that says if we take a partition that's rectangular, or put alternatively, taking a conjugacy class where all the cycles of the permutations have the same length, then this rule is cancellation free, meaning that all the tableau will give the same sign. So, and then indeed, the sum gives the character value simply by a sign and then the number of border strip tableau. And then another result by Springer 10 years earlier says that we can also get these character values for rectangular tableau when we plug in the roots of unity, into the fake degree polynomial. And if we put these together, we get as a result what we just observed, namely that when we plug in roots of unity, that we get the number of border strip tableau, but this result is only up to sign. In our example we had before, all the signs were positive, but it can be possible that this is also negative. So this is the example that we had before. We plugged in the roots of unity and got the cardinality of the set of border strip tableau with fixed strip size. And my goal was to refine this result. To refine this result, of course, we also need to refine first this major index generating function by putting in a second variable, which is t. And then we consider the generating function. We have q to the major index. This is what we had before. And then t to the power of the number of descents. So here we had q to the sum of the descents, and here with t to the number of descents. If we look at the example we had before, here we can see, okay, we had major index 12 and we have 4 descents. So here with this t to the power 4 showing up now. For the next 3, we get always 3 descents, and the last one we have 2, resulting in this nice polynomial. And of course, what we want to do as before is we want to plug in roots of unity. And if we look at the results, the 6th root of unity is not nice because the signs are positive and negative. This is not really what we want to have. But if we look at all the other cases, all the coefficients that are non-zero have the same sign. And so the question is if we have some combinatorial meaning of these polynomials here as well. So if we look at the first root of unity, of course, when we plug in q equals 1, we will simply get the generating function for the number of descents. So this is the number of descents for standard Young tableau. And so the question is there some nice notion of descents on border strip tableau explaining these polynomials here? And the answer is yes, there is. And I will explain you how to define descents on border strip tableau on the next slide. So we look at the big example again. So here's our border strip tableau. And we first want to get rid of most of the labels and just stick with the label that's in the tail of each strip, which is the leftmost cell in the last row of each strip. So we only have here this 1 that's left, here is the 4, etc. And now the notion of descents is quite familiar, what we had before, namely I is called a descent if I plus 1 is in a row strictly below. So 1 is not a descent because 2 is right next to it. 2 is a descent because 3 is here somewhere below. 3 is not because here is 4. 4 is a descent because 5 is below. 5 is a descent because 6 is below, and either 6 or 7 are descents. So this is how we have descents on border strip tableau, but this is not the statistic we are looking for, but an important ingredient to it. The statistic comes now on the next slide, and for this I want to recall you that the height of a strip is the number of rows it spans minus 1. And then the statistic is as follows. We calculate the strip size k times the number of descents plus the height of the strip containing 1. It's easiest to see in this example. So we already calculated the descents. There were 3 of them, 2, 4, and 5. And now we have to get the height of the strip containing 1. So this is this strip here. It spans 2 rows. So the height of it is 2 minus 1, giving 1. And the total statistic is now 3, because that's the strip length, times the number of descents, which is 3, plus 1, which is the height here, giving 10. Let's go back to the example with the partition 2, 2, 2. So if we look at strip size 1, we get back the standard tableau. And here you can notice that the definition of descents on standard tableau and the definition of descents for border strip tableau with strip size 1 coincides. So this is something that's good. The definition of the statistic here is 1, because that's the number of the strip length, times the number of descents, plus 0, because a single cell always has height 0. So if we look here at the values and add them up, we get precisely this one here. So here it's no surprise because this is just a generating function of the descents, and our statistic behaves well when we just look at strip size 1. Looking at strip size 2, here are maybe 2 interesting examples. Here in this guy, we have 1 descent, which is just 1, and the strip height of the strip containing 1 is 0 because it spans 1 row. So here we have the statistic value 2 times, that's the strip length, one descent, plus 0. And looking at this one here, this also has one descent, which is 2, but this time the height of the strip containing 1 is 1. So here we have 2 times 1 plus 1. And if we look at the polynomial that we get here, this is precisely t squared plus t cubed plus t to the power 4. So the sum of these here. K equals 3 is, I think, the example where you can see best what's happening, because here is no descent, but the strip size, the height of the strip containing 1 is 2. So we have t to the power of 2. And here we have 1 descent and the height of 1. So we have t to the power of 4 in total. So this is this polynomial here. And this is the refined result that I wanted to achieve. So if we have a partition, and this time it's important to say that it must have empty core, and we take empty k core to be precise, and we take a primitive k through the unity, and we plug it in, then we get the sign that we already had before from the Murnaghan-Nakayama and James Cabot and Springer results. And then we have here this generating function of the statistic on the border strip tableau. So this is the refined results. And I also want to talk about the proof, and there are some important ingredients here, namely partition quotients. You will see that in the next few slides. Some Schur function identities. Then there's also a nice bijection showing up. And what was also, at least for me, quite important is a huge knowledge resource, which was the Wikipedia by Per Alexanderson. He has this nice metric functions catalog where you can learn actually everything that you need to prove this result.
Speaking of Per Alexanderson, he has a question in the chat. Does the theorem generalize to skew shapes?
Unfortunately not. And I have a slide in the appendix. So if you ask me in the end again, I can show you the counterexample in the appendix. Okay, so this is the refined result, unfortunately not for skew shapes. So the proof steps here on this slide, for the moment, just ignore all the formulas because this is far too much. But in the top box here is just the result that we had. So this is what we want to prove. And the statistic, to recall, this was k times the number of border strip tableau plus the height of the one strip. We will now use something that's called k quotient to manipulate the right side and rewrite this as a different sum. Then we also want to manipulate the left side. For this, we'll use Schur functions and some identities. And then if you take now a look at these sums, they kind of have a similar structure, at least if you look at the powers here with k times a statistic plus whatever this idx is for the moment. And here with t to the power of a multiple of k again, plus something that looks really similar as before. And this already hints that the final part will be indeed a bijection, and you will see this in the end. So let's start with the first part. For this, I told you we need partition quotients. And the idea is that if we have a partition of size n with empty k core, we want to divide it by k. Dividing by k means that we will get now a tuple of partitions, namely k partitions, such that the total size, if I add up the sizes, we get n over k. I don't want to tell you how to get this quotient, but simply use it as a black box. If we have empty k core, we can bijectively map it to a tuple of k partitions with smaller size. So in this example, this is a partition we have seen before. There are here, this has size 21, and here the total size is 21 over 3, which is 7. So this is the free quotient. If we iterate this bijection, one indeed can get a bijection between border strip tableau with strip size k and fillings of the partitions showing up in the k quotient. And we call this fillings then the standard tableau tuple. And I will show you how to do this on the next slide. So first, to be able to iteratively apply this quotient, what we first need to do is we need to make a sequence of partitions out of this one. So what we will start is, we start with the empty partition, and then next is the strip that contains 1. So we look at just the strip, and this is this partition here. Next, we will look at the strips containing 1 and 2 together, and they in total form this partition here. If you also take 3 into account, these 3 are coming to, and here taking 4, we get this one here as well. And in total, we have here this sequence of partitions that correspond to our border strip tableau. And now to each partition, we can take the 3 core, so we get always 3 partitions. And now what we have done from left to right, we can also do it vice versa and read from here some kind of standard tableau. And this works as follows. We just look at where does the next cell come into the core. So here we started with empty, 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 and then we have empty and 1 cell and empty, and this cell here corresponds to this one here. Next, this one shows up, this is this 2 here. Then this one shows up, this is here the 3. This one here gives the 4, and so on. So this is a bijection between a border strip tableau and standard tableau tuple with the shape given by the quotient. Now, of course, it's interesting that we want to recognize descents in the standard tableau tuple, and I've highlighted the descents we had before. And here you can see it's a little bit complicated, or that there seems to be no nice rule what a descent is. And for this, we need a new notation about of partitions. So I've told you about French, English, and Russian notation, and now comes the Austrian notation. So we take our partition and we rotate it by 45 degrees. So it looks like this. And we align the partitions and get this nice grid here. And here we can explain how to read off the descents. The rule is as follows. We compare I and I plus 1. And let's look at 1 and 2 here. 2 is to the right of 1. This is in the second case here. If I plus 1 is to the right, then I plus 1 must be somewhere strictly below to be a descent. So here 1 is not a descent because 2 is to its right, but it's not strictly below. It's on the same level. Let's look at 2 and 3. 3 is to the left of 2. This is the case 1, and it's on the same level, or we can also say it's weakly below of 2. So 2 is a descent. If we look at 3 and 4, 4 is in the same tableau and it's above of 3, so 3 is not a descent. 4 and 5, we can see, okay, 5 is to the right and it's strictly below 4, so 4 is a descent. 5 and 6 is again the case 1 where 6 is to the left and strictly below, so 5 is a descent, and 6 and 7 there's no descent because 7 is above. So this is the Austrian notation, and this notation is super good to compare contents, or called short GOCC.
I like GOCC showing up. I do have one question. I know you explained this in the last slide, but I think I missed something. Where is the the three little tableaus on the right showing up from B? Where do you get, because I saw this comparison, I just wasn't really sure where the stuff on the right was coming from.
Okay, so if we just look at this arrow here, this means take the 3 quotient. So this is the map that kind of divides a partition by 3. So this is then the sequence we end up with. And if we want to go from this sequence to this tableau here, we just need to look from each step, where does the next cell appear?
I guess, yeah, I think it's the quotient that's confusing me. Like how does dividing that by 3 give these 3 different numbers? Like what does that mean exactly?
Okay, let's go back.
I might have just missed some of the details from this slide too.
No problem. So this is something I told you, we will use it as kind of a black box. This is a bijection due to Littlewood, where you can take partitions with empty K core, and then you can kind of divide them by K. And what you will end up with are precisely K partitions, such that the total size is reduced by the factor 1 over K.
Okay, so you're sort of dividing it into these 3 pieces, where one is like the angle, and one is the vertical 2, and one is the horizontal 2.
Yeah. So
and if you changed K, would those shapes change, and would like the number of them change?
Yeah. So if we consider the 3 quotient, we got 3 here. If we consider the 2 quotient, we will get 2.
Yeah, but the exact shapes that they are, does that depend on the details of the theorem that you don't want to get into here, which is totally reasonable?
Yes. So the shapes also depends on K. Yes.
Okay, so somehow you're dividing your object into these 3 different types of shapes, and then in the next slide, so it looks like, so I'm confused why you would have a null set at the beginning for the triangle one, because that looks, or the second one down, I guess it's not exactly a triangle, but that looks exactly like the first of your 3 shapes. So
okay. So we use this partition here and apply the 3 quotient. So what the 3 quotient will do, it will give us 3 partitions such that their total size is the original size divided by 3.
Okay.
So we had original size 3. So we divide the size by 3, giving us 1.
Okay, and then your total is going to be.
So the total must be 1. So there's kind of there are like only 3 choices that we can have here.
Yeah.
Or here or here.
And the way that you figure out which one it is, that's the black box mystery that I'd have to read other stuff to learn the details for, right?
Yes. So
thanks.
It's actually a nice combinatorial construction. It's not hard. And I think the easiest way to see them is something called the abacus model. And I really like this, but I thought there's not enough time.
Yeah, no, and it's totally fair. Sorry to eat up some of your time. If you go over a little bit, that's fine. But I was just curious about some of the stuff. And I think Per sent something in the chat to give some further, like an example for how this is done. So I might look at that later to learn it more. But thank you. And you can keep going on. Oh, we also have a question from Ann Schilling. Can you define a major index statistics from your descents that is equidistributed with the inversion statistics?
I actually don't know. This would be quite interesting to see what the major index is here. I'm aware that there's a paper that defines major index for border strip tableau using position sequences in an abacus, but I'm not quite sure how they would relate and if one of these possible definitions answers Anna's question.
And then Vic Reiner asks, is there a column strict tableau version of this story?
I actually don't know. I did not try to do it, but one could try. Okay, but now let's proceed, I guess. So Austrian notation is good for GOCC. And then also one thing that we of course need to be aware of is that we need to figure out what is the height. This was the second ingredient of our statistics. the height of the strip containing 1. And this is easy to see here because we just need to check the index in which the 1 appears. And the index is counted from right to left, starting with 0, but this is just small detail. So here we count 0, here's 1, here's 2. So we see the 1 is precisely in here, telling us that the height of the border strip containing 1 is 1. So what we have done now is that we are able to use this bijection to rewrite the right-hand side. So the sum over all border strip tableau, where we have our statistic, now becomes the sum over all standard tableau tuple, where we have the number of descents, as I've shown you in this Austrian notation, plus the index where the 1 appears. Now for the left side, we go to Schur functions. And for this, I need to define semi-standard Young tableau. They're quite similar to standard Young tableau, but this time in the rows, the values don't need to be strictly increasing, but only weakly increasing, giving a major difference because now there are infinitely many of those guys. So here are just some of them, and using the standard semi-standard Young tableau, one can define the Schur function simply as the generating function of all the semi-standard Young tableau, where this power I will explain here in this example best. So if we take a semi-standard Young tableau, we associate to this one a monomial by simply saying 1 is mapped to x0, this is x0, and this is mapped to x1, and then we multiply everything together. So we get a x0 squared plus x1. Or maybe let's look at this one here with 1 corresponding to x0, this one corresponds to x1, and here with x2, giving a total of x0 times x1 times x2. And if I sum up all these values, this is the Schur function associated to the partition lambda. And one thing to notice is that if we substitute for our variables just ones and then a bunch of zeros, we also denote this with 1 to the power how many ones I want to have, then this is precisely the number of semi-standard Young tableau with all entries at most m. There is a nice identity that you can get from a paper of Gessel from the 90s that relates the generating function that we are interested in, this f lambda qt, together with a generating function or a sum over the Schur functions where we plug in powers of q for the x's. And then we have here this t to the power of m. And then we divide by something that's called the Pochhammer symbol or q Pochhammer symbol. And this formula is quite nice because we can plug in roots of unity into this one. And we can directly get what we have for the Pochhammer symbol, rewrite everything a little bit, and then the formula looks something like this, where the right-hand side is what we want to focus on next. And to understand the right-hand side or to make something nice out of this, we need to know what we can do with Schur functions when we plug in the powers of roots of unity. Here comes a nice theorem where one particular case already showed up from 2004 in Rainer Stanton's and White's nice paper about the cyclic sieving phenomenon, and I generalized it to work in general. So we take a partition with empty core, we take the quotient, this was this black box, now we have this k partitions, and we have a k fruit of unity. Then we divide m-1 also by k, so this is like a quotient again, and look what's the remainder, so we write m-1 as L times k plus r. And then we can directly write the Schur function evaluated this powers of roots of unity as a product of Schur functions, where now the partitions are precisely the one that are coming from the quotient. And also notice that here's the sign showing up that we had in our theorem. And here we don't have roots of unity anymore, or just the trivial, the first root of unity. We have just here a bunch of ones showing up. And precisely in the last R partitions, we have L plus 1 ones, and then the other one we have just L ones. And the original theorem due to Reines and Y was the case for R equals 0, and the generalization is, at least that I'm aware of, the first one is that it was figured out by me. And if you look at the right-hand side, I've told you that Schur functions where we plug in just ones can be seen as number of standard Young, semi-standard Young tableau. So the right-hand side, except of the sign, counts the number of semi-standard Young tableau tuples, where we take precisely the shapes from the quotient, and the entries are restricted, namely here for the first K minus R partitions, the entries between 2 and L plus 1, and for the rest, the entries are between 1 and L plus 1. And if we now look at what we had before, this was the right-hand side of guessless identity. When we plugged in the roots of unity, we can nicely rewrite this now as a generating function over this semi-standard Young tableau tuple, where in the powers showing up the maximal entry, -1, and we multiply this by k, plus the position of the leftmost one in T. So this result you can obtain if you first multiply in this 1 minus T. This will fix the position of the leftmost one. And then if you multiply in this factor, this will fix the maximal entry. So this was kind of the second step. We used the Schur function identities to get something related with the semi-standard Young tableau tuples. And now the last part is a bijection. So what we want to prove here is on the left-hand side, if we look what we have here, the first factor can be seen as the generating function for compositions that have precisely n over k minus 1 parts, where 0 parts are allowed. Then here we have the generating function for the standard tableau tuple that we got when we iterated the quotient. And here we have the number of descents and the position of the one. And on the right side, we have the semi-standard Young tableau tuples that we had from the Schur identity, where we have the maximal entry -1 and also the position of the leftmost one. So what we can indeed do is we want to get a bijection where we take a composition and a standard tableau tuple and map it to a semi-standard Young tableau tuple. And it should be in such a way that the composition denoted with alpha, that the size of alpha, so the sum of all the entries, plus the number of descents, plus 1, gives the maximal entry on the right side, and the position of the 1 corresponds to the position of the 1. So the bijection works as follows. Here we have our composition. Here we have our standard tableau tuple, and on the right we will construct the tuples of semi-standard Young tableau. And the first thing that's of course fixed is the position of 1, because this is what we want to have because of this condition. For the first few steps, ignore the composition here, we just look at what's going on in the tableau tuple. So we go from 1 to 2. This will tell us that we should put the next entry into this position here. And we see 1 was not a descent. So what we simply will do is we keep writing a 1. Now the next entry should go where the 3 was, and 2 is a descent here. So what we will do is that we will increment the value that we write in here. So instead of 1, we now write a 2. Going from 3 to 4 simply tells us the next value should go in here. And since 3 is not a descent, we will write the same value as before, which is 2. Okay, for now I ignored the composition on the left, and this was okay because I had only zeros here. But now I will tell you what to do with the composition. And it's quite easy. The composition gives us an additional increment. So going from here 4 to 5, we had the descent. This will tell us we should put the next value in here, increment 2 by 1 because we had the descent, and we have to increment 1 additional summand because here we have a 1. So this will be a 4. Now we go from 5 to 6. This was a descent, so we will increment 4 by 1, giving 5, and we will increment by additional 2, giving us 7. And from here, from 6 to 7, the last step was not a descent, so here we will write 7 plus the increment coming from the composition, so 7 plus 2, giving us 9. And one can easily see that this, in fact, is a bijection. And if we just want to go from the semi-standard tuple to the standard tableau tuple, we kind of just need to standardize in a good way. So we go here from the entries from left to right and then simply standardize. Here we get 1, 2, 3, and 4 and get directly this tuple again. So now we have this bijection, and then this bijection links together all these parts. And now we can sum up what we have. So the theorem now is proven that when we have our partition with empty k-core, we can plug in the roots of unity and can interpret these generating function where we had major index and descents on standard tableau now as a generating function using the descents on the border strip tableau. There are some more ideas and questions that I'm interested in what we can maybe do with this. And one thing would be to refine some implicit cyclic sieving phenomena that Per Alexanderson, Martin Ruber, and Joachim Uhlin together with me observed in a preprint that we published earlier this year, where we could prove that f lambda q, where no t is showing up, squared is always a polynomial that comes from a cyclic sieving phenomenon, and similar results. Then of course it would be quite interesting to see if there is some story that relates to cyclic descents, and then it would also be quite interesting to see some representation theoretic meaning. That's all for my talk, and thank you for your attention.
Thank you very much. Let's all do a reaction of clapping or an actual clap. And we had some questions during the talk, but if anyone has additional questions, now's the time to ask.
Okay, yeah, Per asks now, so skew shapes, because he already asked. So let's go to, oh yeah, if you want to know more about partition quotient, here's the link to Per's wiki. The skew shape unfortunately fails. So here's one, I think it's the smallest example. We take these nice Q shapes looking like this, and there's just one border strip tableau with strip size 2, which is I put these together, and these together, and then the labeling is unique. So we only have one border strip tableau. But if we look at the skew generating function and plug in -1, which we would have for the strip size of 2, we get here 3 powers showing up, and unfortunately not 1. So here this fails, but I guess it could, so that there are some instances where it actually works. So maybe one could use some additional statistics, maybe here where we incorporate what we have cut away. I'm not really sure.
Okay, oh, that's interesting.
Okay.
Alex, you're muted.
Oh, sorry, I am muted. Sorry, there's a question from Bruce. If you want to unmute yourself and ask it.
Hi, Stephan.
Hi.
Have you thought about promotion on border tableau, ribbon tableau?
No, I haven't thought about that. But of course, one can define them maybe using local rules. One need to check that because we have the sequence of partitions.
Yeah, yeah, I did check that, but I didn't have anything to do with it, so I haven't written it up.
Okay, but I did not check this, so I have no idea if this really works. Okay, then I think Darcy was asking for the slides. Oh yeah, I wanted to put the link to the slides into the chat.
Yeah, it's probably helpful in general if you have one. Great.
Yes.
And Daria, I know you were 24 hours early, so it's okay if you're a little late now.
Okay.
And then Vic has a question if you want to ask it.
Yeah, sure. Very nice talk, Stephan, by the way.
Thank you.
So these, fake degrees, they show up when you want to write down this bi-Mahonian distribution with two different Qs, and there's a bicyclic sieving phenomenon associated with this bi-Mahonian distribution. I'm just wondering whether if you, those two Qs keep track of major index of a permutation and its inverse. What if you keep track of, with a separate set of T's, the number of descents? Can you plug in roots of unity in the Q's but keep the number of descents around and come up with a, like an analogous nice story to go there? Have you tried that?
Let me think about that. So what I kind of tried, and this is what's related to what I've written here, is this refinement of this CSP result that I multiplied together F lambda QT together with F lambda Q1. And I conjectured that this is an instance, or it's a polynomial for a cyclic sieving phenomenon. And if we add over all shapes lambda, then we kind of get something that looks like a polynomial where we have Q to the major index plus Q to the major index of the inverse. So this is something that's maybe related to this.
Does sound related, but maybe you can be more refined and use two Qs that keep track of the major index of W and major index of W inverse with separate roots of unity. I mean, there is a nice story that goes there.
No, but I did not try that. Yeah, that's something to look at, of course.
Thanks.
All right, well, if there's no more questions, we can thank Stephan again. So thank you very much. That's a great talk. Great way to start out the season 2 of the GOCC. So appreciate that. I'll stop recording and you can ask all of the questions that you don't want on YouTube.